All right, class, we'll get started. So just a few announcements. Safety projects were assigned. I'll send an announcement to Canvas soon, but I put together the projects or assigned the projects for the safety project. And then homework 9 will be due this Wednesday. I know many of you are going to be traveling. I myself am going to be traveling shortly after class on Wednesday morning. But again, everything that you need for homework 9, we covered by last Wednesday in class. And so if you're going to be traveling, you can get started now. Yeah.
It's reached the maximum number of nodes. We have to use thread.
You've reached the maximum number of nodes for what? Oh, yeah. So I went through a couple of them myself, and I haven't heard back from the TAs. But I went through a couple of them, and it looks like it should be okay. If you do run into the issue, so there are 7 different projects that are assigned to 15 groups. So if there may be 1 or 2 where you're going to run into that node problem, especially if you're doing your convergence study. So it's possible that for a few simulations, you do need to run on the grad cluster. But you should be able to do most of your work on the student version at least. Okay. Any other questions? Yeah.
So with homework 9, when we're redoing the from the midterm, will our answers be exactly the same as what they should have been on this? Like I tried doing it on Aspen, and I was getting close to the right answer, but it was like all at like 20% or something.
I have to redo it myself on Aspen. I haven't redone it myself on Aspen. That's on my list earlier this week. But it should be close. 20% sounds a little bit far. Yeah, let me check and I'll get back to you.
Okay.
Okay. All right. Any other questions? Yeah. You will. Yeah. Sorry, we're running down to the end. So okay, a couple things to remind you of. 1, I dropped 2 homeworks, right? So if you absolutely can't get one of these in time, it can be one of your drops. That's fine. I view the homework. I mean, the homework is also 10% of your grade, right? Total. So every single homework is about 1% of your final grade. I'm intending it more as like practice, right? Semi-enforced practice than it is a really major part of your grade, something that's really going to swing your grade one way or another. And since we are covering, we don't have much time left until the final, right? Is what it comes down to. And we are covering new material, right? We're getting into chapter 9. So the homework is going to cover some of chapter 9. And then the last homework, which will be a week after that, we'll cover the rest of chapter 9, basically. So, yeah, I'm sorry, but yes. Yeah. It's a good question. I will check in with the TAs about office hour schedule for the week. Yep. And ask them to make sure they provide office hours one way or another. Yeah. Okay. Other questions? Okay. All right, compressible flow. So we're getting into the last chapter that we're going to cover in this class. This is chapter 9. And we're going to see that a lot of some of the things that we took for granted in chapters 1 through 7 are going to change quite a bit as we get into dealing with the effects of compressibility on fluid flows. But just first, we have some definitions to get out of the way. So today, largely, we'll be talking about some definitions and preliminaries in compressible flow. Then by next class, on Wednesday, we'll get into solving some problems in compressible flow. And we're going to see that there are going to be basically 2 types of problems that we're going to be equipped to solve with what we learn in this class in compressible flow. The first will be determining what the velocity, pressure, temperature, and all the different variables that describe the flow look like when we have flow through a converging, diverging nozzle, or when we have internal compressible flow, and the area changes. that's the first thing we're going to deal with. The second major type of problem that we're going to discuss is what happens when we have supersonic flow and a shock wave, and we'll talk about how to deal with that. But before we get there, again, we have some definitions to get through. So the first is that when the flow speed is comparable to the speed of sound, we're going to have to consider what we call compressible flow. And notice here I said comparable to, not necessarily greater than. Okay, that's going to be important. But one of the characteristics of this is generally difficult to achieve in liquids, right? So we've discussed how typically we treat a liquid as incompressible. So water, we're going to typically treat as incompressible unless we're inside of like a mantis shrimp claw or a snapping shrimp claw, because we generally need a pressure greater than 1,000 atmospheres to have compressibility effects in liquids. But in gases, a pressure ratio of just 2 to 1 from the inlet to the outlet can be enough to cause compressible flow, right? So this is very achievable, right? So for venting to atmospheric, right, we're talking about like 30 psi, right? So basically what's in your car tires can be sufficient to drive a supersonic flow. So shock waves, which you see visualized here, we're going to see a lot of visualizations of shock waves coming from an album Fluid Motion here. Shock waves are often a defining feature, not always, but often a defining feature of compressible flow. So when we do have supersonic flow, as in flow that's greater, or the velocity of the flow is greater than the speed of sound, then we will often get shock waves. We're going to talk a little bit more about how to handle some of this, but this is a visualization of a shock wave inside of a model rocket nozzle. And you can see that all of these kind of hard boundaries here are shock waves, and there's this really complex pattern of shock waves that's formed, and they're reflecting and interacting with one another as we move through this nozzle. And this is an example in an external supersonic flow, where we can see, first of all, this big circular shape here is a shock wave. We call it a bow shock, a shock out in front of the object. We can actually see that shock interacting with the edge of the wind tunnel that was used and bouncing off, reflecting off. And then we can see a number of different shocks in the wake as well. So shock waves are often a defining feature of a compressible flow when that flow becomes supersonic. And the things that we're going to talk about here, so previously we separated internal and external flow. Here we're going to talk about, in general, some basic principles of compressible flow that are applicable both for internal flow, as in pipes, nozzles, right? Like that's internal to a rocket nozzle, and external flow, like flow over airfoils, or I don't know, I guess if you had a supersonic turbine or something. So we're going to talk. So the things we're going to discuss here will apply generally. And really, this is just one chapter of something that could be, an entire course of graduate study or something, right? So we're really just getting a brief flavor to compressible flow here. So as always, we're going to use dimensional analysis and dimensionless numbers to kind of guide our discussion here. And the important one is something that we discussed in the first week, but we're going to define it a little bit more rigorously here. In particular, we're going to talk about the speed of sound a little bit more rigorously. And this is the Mach number, written as MA, and it's the velocity, the characteristic velocity in the flow. So maybe it's the average velocity or typical velocity within, or it's the velocity within a section of pipe. It's the velocity of an object moving through the air, divided by A, which is the speed of sound. Okay. And so this is the Mach number, written as V over A. It's just a velocity, right, over a velocity, so it's dimensionless. Yeah, so it's the characteristic flow speed over the speed of sound. And remember that up until now, we've considered Mach number, we said much less than 1. We're going to put stricter limits on this today, but we've considered Mach number much less than 1 which we said was valid for the case of or led us to this case of incompressible flow, which simplified greatly our mass balance equations, right? Our statements of mass conservation. Right, for example, remember that in incompressible flow, the velocity basically dropped out of our statements of mass conservation. In compressible flow, that's no longer going to be the case. And when we had Mach number much less than 1, we also had constant density. So in compressible flow, this is no longer going to be the case. Density is going to become a variable. So we're going to consider other regimes where density can vary. So I just want to look qualitatively at what those other regimes are, and we'll define them in terms of Mach number. So in practice, we're going to say Mach number less than about 0.3. For Mach number less than about 0.3, we can use the incompressible flow equations with little error. Okay, so when we say much less than 1, really we mean less than about 0.3 or so in the case of Mach number. When we get to Mach number between 0.3 and 0.8, this is still subsonic flow. So when the Mach number is equal to 1, we have a flow where the characteristic velocity is equal to the speed of sound. We call that sonic flow. So anything less than that is subsonic, right? Is less than sonic, subsonic flow. And in this regime, even though we're subsonic, density, the effects of density and compressibility are important, but we're not generally going to have shock waves forming within the system. So it may not look like we have, we're not going to have those characteristic shock waves that indicate that we definitely have compressible flow. But nonetheless, our incompressible equations of fluid motion do not work in this regime. For Mach number from 0.8 to about 1.2, which is right around that sonic region, right around Mach number equal to 1, we call this transonic flow. So in this type of regime, shocks appear within the flow, and we'll typically have both super and subsonic flow regions. So that image, see if I can turn. Here we go. So that's an image of of the shape moving through fluid at Mach number 0.84. It's being visualized using a technique called Schlieren that can actually see the differences in density within the fluid. So it's actually seeing basically compressibility of the fluid. That's what causes the contrast. If you look in the wake, you can actually see these ripples. Those ripples are differences in density within the fluid, and they're being visualized directly using this technique called Schlieren. Actually, most of this entire right side is going to fill up with visualizations of supersonic flow that were all generated with the same kind of technique. And you can see in that image that that shape is, even though it's traveling at a subsonic speed, we are starting to see some effects of compressibility in that flow. As we push up to Mach number of just 0.885, right? So we're still definitely subsonic. The overall velocity of that of the shape is still subsonic, but nonetheless we can see little tiny shock waves happening. Right. So what's happening is that the flow. So even though the characteristic velocity is subsonic, the flow locally in some of these areas here around these corners, right? That flow is accelerating to the point where right there, it's exceeding the speed of sound, and we have a little shock wave forming. Right? You see that? And so even though the characteristic velocity is subsonic, we can still have shock waves within this flow. Finally, we get up to this Mach number of 0.99. This one looks a little bit darker. This visualization is a little bit darker, but nonetheless, we can see quite distinct shock waves forming here, even though, again, based on characteristic velocity, we're still subsonic, because locally the flow is accelerating past the speed of sound in certain regions. And then finally, we get to Mach number of just over 1. And now we can see the creation of this distinct shock wave out in front, right? As well as these later shocks. So for Mach number between 1.2 and 3, that's when we're in this supersonic flow, fully within the supersonic flow regime. Here we're going to see shock waves form, and typically there will be no subsonic region within the flow. So here we have this tapered shape at 1.84 with a sharp nose, and here we can see these really distinct sharp shock waves forming. That's more characteristic of fully supersonic flow. And then for Mach number greater than 3, we call this hypersonic flow. This is where we have really strong shocks. So this is, yeah, the same basic idea, same basic kind of visualization, but now it's on a background of these contrasting stripes. So you can really see what's going on very clearly. This is Mach number 5.7. We can see a really, really strong shock wave forming. Okay. So we're going to talk about what happens across a shock wave and how we can determine the velocity, density, temperature, and pressure across a shock wave. But just qualitatively, I'm saying this, we can see a really strong shock here. So we can see this really distinct band with a really large disturbance, right? A really large optical disturbance as we move across it. And that means that there's a large difference in density. And this technique, the Schlieren technique, is visualizing differences in density. And so we can actually tell that this is a really strong shock just because it looks like such a large disturbance, or because we have such a big disruption in what the image looks like in that region. So as I'm saying, like, oh yeah, we can see that this is a really big shock. That's what I'm looking at. Okay, but we'll look at ways to analyze that and actually put a number onto what the difference in density is. Yeah.
This is more like a kind of curiosity question, but so if you have like an explosion, like a nuclear explosion or any kind of bomb, have like a shock wave coming, is that usually supersonic or hyper?
Oh, interesting. Certainly supersonic, right? So the question is, if you have some kind of an explosion, is that is the shock wave typically supersonic or hypersonic? You know, I'm not positive.
Okay.
Yeah, certainly supersonic somewhere in this regime. Yeah. But yeah, good question. Yeah, so yeah, same thing. If you look at like footage of something like that, you can actually see the density difference in the air on either side of the shock wave as it moves over objects in the distance. Yeah. Any other questions? Yes.
I was wondering about the, I've heard that when you're like any velocity where like the air is not driving up drag where it can't accelerate anymore.
Mhm.
And I was wondering, like, is that at like this kind of like supersonic speed or something? Because like it feels like if we can get an object like that circle or like that pointed triangle thing, you could go like supersonic speed, like you just make it sharper and then it can go faster, like that make terminal velocity or no.
Yeah. So the question is like, is terminal velocity typically supersonic, and does an object becoming supersonic mean that it doesn't have a terminal velocity, or something like that? And so terminal velocity would mean that when we have an object falling at a rate such that the drag force going up is equal to the gravitational force pointing down. For most things, everything that I'm aware of on Earth, terminal velocity is subsonic. And so all the analysis of our previous chapter 7, would actually be sufficient to determine the terminal velocity. You know, so like when Felix Baumgartner like fell out of, jumped out of a capsule basically at the edge of space and fell towards Earth, he reached terminal velocity, right? Fairly quickly. And actually that terminal velocity would change as he fell closer to the Earth. Why would it change as he fell closer to the Earth?
Just because like the difference in pressure, the atmosphere.
And density, right? So definitely differences in pressure, right? And the important variable here is the difference in density as he's falling through the atmosphere, right?
That changes because like the actual makeup of like the atmosphere, because we're incompressible, we're dealing with incompressible atmosphere.
But the difference in density is just as you're falling from such a high elevation, you're falling through atmosphere that's very, very thin down to thicker and thicker air. And so there's physically, one way to think of it intuitively is like there's physically less at high altitude, there's physically less air for you to bump into. And so terminal velocity would be higher, right? But still subsonic.
But you have some kind of stress or something like if you propelling through the air to essentially get faster than the velocity. Not with gravity.
Definitely, or and for a falling object, actually, like something re-entering from space, right, will absolutely reach hypersonic speeds, right? So for like a capsule coming back from space, like Mach number of 25 would not be out of the question. Okay, so we're talking incredibly strong shocks. So we'll see when we talk about shock waves, we'll see that one of the effects of a shock wave, especially a really strong shock wave, but even a weak shock wave, is that we'll see an increase in temperature as we move across that shock. And that increase in temperature is actually really the main reason why you need heat shields on like a re-entering spacecraft, right? Because there can be such a dramatic, if you have Mach number of 25, there's such a dramatic increase in temperature across this kind of a shock wave that you need to protect whatever's there. Yeah. Okay, any other questions? Okay. No.
It's like with the fact that like the Earth itself is only moving at supersonic. I imagine it's moving at supersonic speed. But is the reason why it's not supersonic because the gravitational force of the planet?
Yeah. So the question is, the Earth is moving at supersonic speeds. So is the reason that gravitational force is keeping everything? Yeah. So the reason is that gravity is keeping the atmosphere with the Earth. And so the relative velocity of the Earth relative to its atmosphere is, the speed of weather, right? So, the speed of a cold front moving across the continent. So it's definitely subsonic.
Okay.
Yeah. I mean, that's how fast the air is moving relative to the Earth. Okay, so we need to consider conservation laws, and we need to reconsider our conservation laws now that we're going to be looking at compressible flows, right? So this means going back to chapters 3 and 4 and removing that constraint of density being constant, right? Which helped us out quite a bit. Now, I will say that primarily, like in this chapter, we're really just going to be looking at like chapter 3 stuff applied to compressible flow. We're going to be looking at like mass momentum and energy balances across control volumes. We're not going to be doing a differential equation analysis of supersonic flow. I believe at least one of the projects does involve a CFD of a compressible flow, right? So we can use differential equations of fluid motion with density being a variable in order to make calculations for how the velocity changes within flow around some complex shape, right? So we could do CFD to figure out the details of the entire flow around this kind of an object. In fact, you could do details to do flow around that object in the top right to predict when and where shocks would be forming, right? And to figure out, is Mach 0.885 sufficient to have the formation of shocks on that kind of a shape? And that would require the differential equations of fluid motion for a compressible fluid. But just to get started on our understanding and analysis of compressible flow, in this chapter, we're primarily going to be confined to a control volume type approach, like what we did in chapter 3. Okay. But that still means we need conservation laws. So characteristic of compressible flow is that density changes, right? Density is no longer constant when we have a compressible flow. And so if we look think back to our equations of motion, we're going to have a closure problem, as we're going to have, we now have more variables than we have equations. And so we're going to need to solve some equation of state, some thermodynamic equation of state, in order to find the density and relate density, for example, back to pressure, in this case, temperature, right? So we might use an ideal gas law. And typically in this chapter, we're going to confine ourselves to ideal gases. And that change in density means temperature also changes. And so we're going to need to solve the energy equation. So, so when we consider what are the conservation laws for compressible flow, we're going to have mass conservation or continuity. But remember, this is going to be the form of mass conservation in which velocity appears, right? Velocity does not drop out. So we're going to have mass conservation, right? Density is not going to drop out of our mass conservation equation. We're going to have momentum conservation. Sorry, I keep saying velocity drops out. Velocity never dropped out of our mass conservation. Density dropped out of our mass conservation. Apologies. Sorry if that was confusing. I think I've been saying that all class. So and nobody caught me on it. You should really catch me on that. Yeah, sorry, density. Sorry, in incompressible mass conservation, we ended up with something like velocity times area was, at the inlet would be equal to velocity times area at the outlet for one inlet, one outlet, meaning density dropped out, right? So the mass part dropped out of our mass conservation, which was kind of strange. In compressible flow, that's not the case, right? In compressible flow, density is going to remain. Sorry about that. Okay. Momentum conservation, right? So we're going to have to also consider momentum conservation. But then, as noted, since we have density now as a variable, we need another equation to relate density to our other to the other variables within our system. So we're going to use this equation of state, and then that equation of state involves temperature. So we have to include an energy balance as well. Okay, so we now have, right, remember for the incompressible case, we were generally just concerned with mass and momentum conservation, but now we have to include all four of these sets of equations, right? Actually, all four of these, noting that this is a vector equation, momentum is a vector equation, and so this is really three in disguise. So another parameter that we're going to need to consider is the specific heat ratio. In this class, we're going to denote it as K, which will be Cp over Cv. This is the ratio of specific heat at constant pressure to specific heat at constant volume. For air, which we're often going to be dealing with, we have a specific heat ratio of 1.4. So that's a number that we're going to be plugging into a lot of the relationships. We're going to see that we're going to end up with quite a few of our relationships in compressible flow are going to involve this specific heat ratio. So knowing that specific heat ratio of air is 1.4 can be handy. And note, this K is not thermal conductivity. Okay, that's another case of variables running into each other. This K here is going to be specific heat ratio. What do you use for thermal conductivity and heat transfer? Okay, obviously, yeah, okay. Yeah, but we're not using, this is K. Okay, so we're generally going to consider perfect gases. So it's an ideal gas, by which we mean an ideal gas with constant specific heats. So we're going to say P is equal to rho RT, where R is Cp minus Cv, which is a constant, and K is also going to be a constant. So for air, K is going to be 1.4, and we're just going to leave it there. So note, however, that in this expression and in the nomenclature in your textbook, draw your attention to this, that R is not the universal gas constant. It's not 8314. It's The R here is sometimes called the mass specific gas constant or the individual gas constant. And it's the universal gas constant divided by the molar weight of your gas. Okay. I'm saying all the letters are now different. Yeah, so forget everything you learned in thermo and heat transfer. Yeah. T is still temperature, yes. I think that's true across all your classes. Yeah. So for air, right, we consider molecular weight of 28.97 on average. We get 287 meter squared per second squared Kelvin. Yeah. The question is it only for compressible flows that we use the universal gas constant? So the only time where we're going to be considering an equation of state in this class is for compressible flows. So, and this is generally the equation of state that we're going to be using. Actually, for all of our analysis, we're going to be using this equation of state. So in this class, when we say R, we do mean this individual gas constant. Yeah. And in particular, in your textbook, when we see R, we're using this individual gas constant. So therefore, in my slides, when we see R, I'm using this individual gas constant. Yeah, in the back, sorry. They are, yeah, they are tabulated in the book. I mean, look up the molecular weight as well and compute it. A lot of times we're going to be dealing with air, right? There's enough complexity here that a lot of our analysis is going to be confined to air. And so just knowing R is 287 in SI for air will get you a long way. Yep. Yeah. So if we had, so where this would come from, right? If we had a PV is nRT, right? Where R or NR universal times T, right? You can rearrange, you pull the volume down, right? And then you end up with what should we call it? Pull the volume down and you're gonna have a factor of the molar weight of the gas, right? And then you have the mass of the gas divided by the volume. That's how you end up with rho. And then you end up with this thing that looks like universal gas constant divided by the molar weight of the gas, right? Is your extra factor there. So we use this form here because it's more convenient when we're dealing with fluids, right? Because this relates now all of the things that we have conservation laws for, right? So we have pressure, which we're used to dealing with from momentum conservation, right? Density, which is the thing that we know is going to vary within a compressible flow. It's like our definition of compressible flow. And temperature, which we're going to be dealing with from energy conservation, right? And everything else is really just our universal over the molecular weight of the gas. And it's going to be a constant for a given gas that we're using. And so this is a more convenient form for us to use. That's all. Okay. Yeah.
So how reliable is the ideal and perfect gas law in these issues? It seems like you really wouldn't. Is that fine?
Yeah, I think there's some data on the previous slide. Right. So this is looking at the specific heat ratio, right, as a function of temperature in Rankine. Wouldn't have been my choice. And we can see that this scale is only from 1 to 1.7, right? So this is, even though we see quite a bit of variation, or these curves move quite a bit, the scale is pretty compressed. And the so here is air and nitrogen. So we can see there's certainly some variation, right? As we get up to really high temperatures, there's some variation, but we'd have to have actually fairly strong shock wave in order to get up to these high temperatures. So if you if you were truly trying to analyze the flow around a some object entering from space and traveling at Mach number 25, you might get up to some of these crazy temperatures. and therefore need to consider non-constant specific heats.
Right. With like the rest of the laws are going to the extent that they conflict with like the specific heats.
Yeah, so everything else we're going to do is now going to involve, we're going to take that assumption and carry it forward. So all of those things would depend on constant specific heats.
Okay.
And so all of those things would be invalid for the case of non-constant specific heats.
Okay.
But if you're considering compressible flow or compressibility effects inside of a pipe or a fitting, we'll talk about that, then this is going to be generally a pretty good assumption. So those shock waves are not going to be crazy strong. Yeah. So if you're getting to hypersonics, this is maybe not such a good assumption, but transonic, supersonic, up to that kind of range, this is generally going to be pretty good.
Okay.
Yeah. Other questions? Good question. Okay. And this is just noting that, if we know R and we know K, we can solve for example, CV or CP from these relationships as well. Okay. So to start to make our way towards using these things, we have, we're gonna have to do a little bit of thermo in this class as well. Yeah, it's almost like all of these things are talking about interrelated processes. Yeah. So for a perfect gas, we can compute the internal energy change, right, using CV, right? So again, assuming that CV is constant, we can write our internal energy change as just CV times the delta T, or our enthalpy change as CP times delta T. Again, if specific heats were not constant, we would have to integrate. Right, so this is the form that we would use. But assuming that we have a perfect gas, right, constant specific heats, then we can use this kind of a relationship. So we can also look at this would be so we'll get to enthalpy change. We can compute enthalpy change, right, based on change in entropy, as TdS is dH minus dP over rho. We know that dH is Cp times dt, right, from our relationship of the previous slide. And for a perfect gas, we can pull that rho over, and we have rho T is P over R, right, just a rearrangement of our ideal gas equation. And now then we can integrate from some point 1 to some point 2 and write this in integral form. And now assuming constant CP, right, this pulls out of the expression, and then we can actually integrate this, and we'll end up with the following. So the difference in entropy is related to the differences in temperatures and differences in pressures from points and differences in density from point 1 to point 2. And here I'm just noting that if CP is not constant, or if we don't have a perfect gas, then that's when we start getting into gas tables, right, to make some approximation, or software, right? So there are solvers we can use to solve compressible flow problems that would have all of this information, thermodynamic property information built in, that we could use. But for our analysis, we're going to be confining ourselves to, right, this perfect gas model. So CP, CV constant. Now we will often, not always, but we will often assume isentropic flow. So this is going to be one of our first assumptions that we're going to be making, that we are later going to walk back for certain cases. Okay, so I just want you to note that we're not always going to be considering isentropic flow. In fact, one of the big, we'll talk about this more when we get to solving problems, but one of the big assumptions to watch out for, one of the big decisions you're going to have to make, in fact, one of the main decisions you're going to have to make in analyzing a compressible flow problem is it isentropic or not? Okay. But when we have isentropic flow, right, S2 is equal to S1. And so we have this expression for an isentropic perfect gas. We can relate the pressures to the temperatures with this factor of the specific heat ratios, right? Sorry, the exponent of the specific heat ratios, or the densities. Okay. So what this means is if we have a compressible flow and it is moving isentropically from a region at some P1 to another region at some P2, if I know the temperature at T1, I can then solve for the temperature T2 using this expression. Okay. This is going to be an important expression for us, again, for an isentropic perfect gas. We're generally going to consider perfect gas, so that's not one that we're going to worry about that much, but isentropic is something to pay attention to. All right, so to go further, so this is the first expression that we're going to really be using in solving problems. But to go a little bit further, we have to get a little bit more, a little bit stricter about our definition of the speed of sound. So we're going to have to talk about speed of sound, where it comes from, and what it is. Speed of sound is the speed of propagation of a small pressure pulse in a still fluid. That's what we mean by speed of sound. So this is an illustration from, or a short video from a little clip from Wikipedia showing a small pulse, like a sound wave moving through a medium, right? And this is what sound is. Sound is a small compression of or a small change, small disturbance in density that travels through that medium. And here it's represented by a small compressing and stretching of that grid as it moves through, right? So as I'm talking to you, or you're listening in on the video or something, right? What you're actually hearing are sound waves. What you're actually hearing are, right, compressions and rarefactions within the air. We need to know what the speed of sound is, though, in order to continue our analysis. So to find the speed of sound, we're going to look at the derivation of the speed of sound, which is done by considering that we have some sound wave that's moving at some unknown velocity that we want to find. And we're basically going to do a control volume analysis around this sound wave. But we're going to sit in a frame of reference moving with that sound wave. So in this little clip, imagine that we're moving at this velocity downstream, right? And just following along with this pulse. And now we're going to do mass momentum energy balance on either side of that sound wave. So we're changing our reference frame to move with the wave, right? We're moving at the speed of sound down the room, much faster than I'm going. So now the question is now, what is the speed C? So if we have some fixed wave, given that we have some wave that's fixed in our frame of reference, what is our speed C? We don't know where to start. It's always a good idea to start with continuity. So that's where we're going to start. So rho times A times the velocity, which in this case is just C, right, on one side, is equal to rho plus delta rho times A times C minus delta V. So we're just relating the, assuming that we have some, known, let's say, conditions upstream, we have some conditions downstream that are different by a certain amount. We don't yet know what those are, and we want to find, and we can relate them this way. So delta V is C times delta rho over rho plus delta rho. So now we move to a momentum balance. So again, this is chapter 3 stuff, just applied to compressible flow. So some of the forces acting in the positive X or in the rightward direction is m dot times V out minus V in. And again, we can plug it all in, right? So the sum of the forces here is just going to be caused by any difference in pressure. And this is our statement of momentum change, right, across that shock wave. So pressure forces balanced by change in momentum. In this case, the area cancels, and we're going to end up with this expression: delta P is rho times C, the thing we're trying to find, times delta V. So, and we're going to consider the case of a small change in velocity and therefore a small pressure change. So when we combine this with mass balance, we end up with C squared delta P over delta rho, 1 plus delta rho over rho. And we're going to take the limit as delta rho goes to 0. So if we have this delta rho going to 0, this delta rho going to 0, we'll end up with C. So C here was the velocity of that of the shock wave as it moves. Now, as the difference in density across that shock wave, across that wave rather, not shock wave, across that wave, as the difference in density goes to 0, and the limit of that density change, that density difference going to 0, and the limit of having a very, very small disturbance, then that speed of that wave, the speed at which that wave is traveling, becomes the speed of sound. This is how we define the speed of sound. It's the propagation velocity of a very, very weak disturbance in pressure. So very, very weak means delta rho goes to 0. We end up with A squared is d rho, dP over d rho. The process is adiabatic, right? So we're going to assume there's no change in temperature. And so we can write this expression as follows. Start for more thermo. And then for a perfect gas, we plug in our perfect gas expression, we end up with speed of sound, square root of kRT. Okay, so this is our important result from this derivation. Okay, so speed of sound is square root of kRT. For air, if we're working in SI units, or speed is in meters per second, temperature is measured in Kelvin, then the speed of sound is about 20 times the square root of temperature. Okay. Yep.
Does the velocity have any like effect on the speed of sound, or people are given very distant like sound waves to move through the
Yeah, it does not enter in. It's primarily an effect of density. All right, so it's primarily an effect of how close are the molecules together to transfer the pulse from one molecule to the other. So yeah, it is really primarily just about density. Yep.
So we're looking at Mach number. We're looking at the speed of sound at like a normal speed of sound, like a normal kind of density of the fluid. Right? Like obviously, speed up and get compressible. We're gonna have a change in velocity or in density, which means we're gonna have a change in what the speed of sound is in the fluid. Right?
Yeah, so we're going to see that Mach number. So just as in for external flow, we had Reynolds number was a variable, right? It can change as we move, for example, down a plate, right? We had Reynolds number based on X. We're going to have Mach number that varies, or sorry, Mach number is going to be based on a local speed of sound when we're solving some problems. So yes, as temperature within our system changes, then, for example, if we move across a shock wave, temperature goes up. The speed of sound will change as well as we move across a shock wave. And so our analysis has to include that as well. Yeah. Yeah, so C was the velocity of this wave that's moving, and we haven't yet assumed that it is infinitesimally small. Okay, so maybe I'm yelling really loud, and so there's a larger disturbance that would affect the velocity of that wave. Okay, so for air, this is often convenient. For other materials, I believe this is actually, the temperature needs to be specified here. I believe it's at 20 degrees C, but I have to check. But for other materials, we can see, the speed of sound. Generally, it's going to be lower in gases than in liquids than in solids, right? Because again, primarily this is an impact or primarily the speed of sound is impacted by density of the material, right? In a solid, the molecules don't have very far to go before contacting the next one and transmitting the pressure pulse, right, downstream. So in solids, the speed of sound tends to be really, really much higher, right? In liquids, we tend to be a little bit higher than we are in gases as well. Okay, any questions from here? All right, then we're gonna break here for today, pick up on Wednesday and start talking about how to use what we've developed to solve problems for isentropic flow of compressible fluids. Thank you all.